Assalamualaikum. In today's episode, we solve a problem involving rotational inelastic collision. Specifically, computing the final angular speed of a system of two disks initially rotating with certain angular speed and colliding inelastically. We also wish to determine the fraction of the initial rotational kinetic energy that remains as rotational kinetic energy after the disks have come to their final common angular speed. So just hang on till the end of this video, watch and learn. Question is, in the situation shown, suppose disk A has a moment of inertia I sub A and initial angular speed omega sub A, while this B has moment of inertia I sub A over 4 and initial angular speed omega sub A over 2. Initially, this A and B are rotating in the same direction. Question letter A, what is the final common angular speed of the two disks? Question letter B, what fraction of the initial rotational kinetic energy remains as rotational kinetic energy after the disks have come to their final common angular speed? The right figure shows two disks with varying moments of inertia and varying angular speeds, but the same direction of rotation. Forces F and negative F are along the axis of rotation and thus exert no torque about this axis on either disk. When the net external torque is zero, we say that the angular momentum is conserved. So the total angular momentum of the two disks before they collide must be equal to the total angular momentum after they collide. So in this problem, we are given the following information. This A has a moment of inertia equal to I sub A, and with an angular speed of omega sub A. Similarly, this B has a moment of inertia that is equal to 1/4 of the moment of inertia of this A and an angular speed of 1/2 the angular speed of this A. Our first target variable, that's in part A, is the final angular speed omega. So this is the angular speed of the two disks after they collide. And we base this on the concept of the law of conservation of angular momentum, which when written mathematically, okay, we have this equation. I sub A times omega sub A represents the angular momentum of this A before the collision, plus the angular momentum of this B before the collision, which is equal to I sub A over 4 times omega sub A over 2. And their sum will be equated to the total angular momentum after the collision. 5 over 4 times I sub A represents the total moment of inertia of the two disks. So multiplying it by omega, then the whole term represents the what we call angular momentum after the collision. And isolating omega, since that is our target variable, we have this working formula. I sub a times omega sub a plus I sub a over 4 times omega sub a over 2 divided by 5 over 4 times I sub a. And simplifying, or that will be later, okay, in part B, you also want to determine the ratio of the total kinetic energy after collision over the total rotational kinetic energy before the collision, right? We also take note that since it is an inelastic collision, kinetic energy is not conserved, right? So later, after we have computed for the total kinetic energy before the collision, when compared to the total kinetic energy after the collision, Ke is or should be greater than Ke prime. Moving on to our computation. In part A, determining the angular final speed of the two body system. So omega equals quantity 1 or I sub a times omega sub a plus 1/8 times I sub a omega sub a all over 5/4 I sub a. Simplifying, omega equals I sub a times omega sub a times 9 over 8 divided by 5 over 4 I sub a. And canceling I sub a, we get 9 over 10 omega sub a. Or expressing the answer in decimal, we have the final angular speed of the two-body system after the inelastic collision. We have omega equals 0.90 times omegas of A. Moving on to our computation, we determine the total kinetic energy before the collision. So that's just 1/2 the moment of inertia of this A times the square of its angular speed plus that of this B, all right, whose moment of inertia is 1/4 that of this A, all right, and whose angular speed is 1/2 the angular speed of this A. Hence, its kinetic energy before the collision is 1/2 times I sub A over 4 times omega sub A over 2, right? And that will be squared. So when we simplify by multiplying 1/2 times 1/4 times 1/2 squared, that gives us 1 over 32. All right, so this term here becomes 1 over 32 I sub A times the square of omega sub A. Of course, this term represents the kinetic energy, rotational kinetic energy of this A before the collision. So when we add these two kinetic energies, right, we factor out since both terms have omega sub A squared. So omega sub A squared is factored out, and that will be multiplied by quantity 1/2 I sub A plus 1 over 32 I sub A. And simplifying further by expressing the fractions in decimals, we get omega sub A squared times quantity 0.5 I sub A plus 0.03 I sub A. So we finally get the total angular or rotational kinetic energy of the two bodies before the collision equal to 0.53 I sub A times the square of the angular speed omega sub A. Similarly, we also calculate for the total rotational kinetic energy of the system after the collision. So K prime is equal to 1/2 the total moment of inertia 5 over 4 I sub A times the square of their common angular speed 0.90 omega sub A. Simplifying, that becomes 5 over 8 I sub A times 0.81 omega sub A squared, which when expressed in decimal, we get Ka prime equals 0.51 I sub A times omega sub A squared. So we can now determine the ratio Ka prime over Ke, or the ratio of the final rotational kinetic energy over the total initial kinetic energy. And we just divide 0.51 I sub A times omega sub A squared by 0.53 I sub A multiplied by omega sub A squared. So we get the ratio equal to 0.96, which means that 96% of the original total kinetic energy of the two disks, all right, still remain as rotational kinetic energy, right, after the collision. Or only 4% of the original total rotational kinetic energy has in fact been converted to other forms of energy, such as thermal energy. And that concludes our video tutorial for this topic. Till the next episode, mabuhay. MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.